Hello everyone, and welcome to my talk about the Elvish language, aka templates, concepts, etc. A few words about myself. I'm Dathskovsky. I'm working at an exciting startup called Speed.io, and we are developing the next big thing in big data. We are developing a new CPU that will accelerate analytic for big data. So it's something really huge, and you will hear about it soon, I think. Beside that, I'm also a co-organizer for Haifa C++ meetups, and I'm volunteering in the organization of Core C++ 2023. I know you're in the C++ conference right now, but Core C++ is just behind the corner, and there still are tickets. So if you want to visit Israel and see very interesting talks, this is the time to do it. And we have a very interesting program. Bjarne is going to be there this year. Right, now let's start. What is the first thing that comes in mind when you think about templates? Or most people, when they hear this horrible, horrific word, templates, what do you think? What comes to your mind?
Clean code.
Thank you, but you're not most of people, right? Anyone else? Yes?
Complex error message.
True. We will get there. Anyone else?
Coding the headers.
Coding what?
Header files.
Coding in header files. That's true. Yes.
Multi-kilobyte type names.
I like you. Okay. So most people, when they hear this horrific word templates, that's what they think. They're looking at it, they're horrified, they don't know what to do with it, and I don't understand why. I will start with this short story. In my previous company, I worked at Abbott, and there I have to create a pluggable system for intracardiac ultrasound. To do that, I had to do everything with template metaprogramming, generic programming, and I created it. The problem was, it was pretty simple to me, but most people that worked with me in my team, when they used to see a problem with the templates, they would just come to me and say, Alex, I don't know what to do with this. You fix it. You wrote it, you fix it. And that's most of the people when they're here and see template code, for some reason, they're afraid, they just don't want to keep working on it. They think it's something impossible, and they're just throwing to the author instead of just understanding it. So I hope that after this talk, most of you, and again, this is C++ now, so most of you like templates, right? So I'm preaching to the choir here, right? So you will go to your jobs and you will tell people, hey, look at what Alex did, and see his talk on CppNow, CppCon, CppCore, wherever you want to look at it, watch it, and see the templates are not that bad. And if you have access to C++20, it's going to be even easier. So usually, I already gave this talk twice. Usually, I start with basic template rules, just to warm up. But this is CppNow, right? There's nothing basic about it. Let's start with a cliffhanger. Let's look at this code. What do you think it does? Take a moment. Yes?
That provides substitution failure for looking up the return type of a function.
What type of a function?
The return type of, I guess, a function template parameter, right?
It's a function, but it's a special type of a function. It's a member function pointer. But what is special about it? There is something special. You can get the return type even if you're not providing the parameters to the function. So that's exactly what this code does. You're just saying, okay, this function is something that can receive any number of parameters. I don't care about it. Just give me the return type. Yes, please. With function parameter overloading?
You have an overload set.
I understand what you're saying. It doesn't care about the arguments. So if you will give it a function, it will just try to take it, and if it will be overloaded, it doesn't care because you will see it here. You don't provide the arguments. Yes?
I think the arguments have to be copyable because you didn't take them by already reference or by forwarding reference.
That's true, but this is just a toy example. Just wanted to start with something that is more interesting to the audience here, right? So what can we do with this thing? We can create two classes, like we see here. We have struct x and struct y, and they both have a function called add. In one class, we have two integers, a and b, and in the second class, we have a double that we're just adding one, but the function called the same. Because we're just starting the talk, we don't know what traits are, so we will create our own trait called isSame. And this trait is just creating a new struct that's called isSame that has a Boolean inside it. And this Boolean will tell us if the types are same or not, because we're creating a partial specialization for the class. So if both types are u and u, then it's going to be true. If it's something else, if it's t and u, it's going to be false. And then we can use it inside static asserts, for example, here. We're using isSame, decal type on the function with the foo and the function name, just the function name. And we want to say if the return type is an integer or the return type is a double. So if we are using x, the return type is going to be an integer. If we are using y, the return type is going to be a double. And as you can see here, I don't care about the parameter list. It's something very strong if you need just the return type and you don't need the parameter list for it. Let's digest it a little bit. What have we done here? So we have created a class that's called result. This class can receive any template parameter type. We don't care about it. And then we have a specialization for that class. In this specialization, we're saying there's an R, a return type, and there's a list of arguments, which I don't care about. But this class will be initialized if and only if I'm provided with a function. And only then we will have an R type, a type inside it, and res will be well defined only if we have received a function inside it. Afterwards, we need to create a special function that is just a helper, because it's easier to provide a function pointer or anything into a function because the deduction of types is easier there. M is basically the type of the function itself, and T is the type of the class. And this is just MT double, I forgot the name of that, pointer to PM. This is just how you create function members or provide function member to the class. We could do it simpler. We don't actually need to provide this res type that we created here. We already have something in the standard that's called function, and function has a return type. So if we would do it without the res type, all we had to do is just create the same function that receives the same parameters, but the trailing return will use function with the type m, and we will get the result type from it. We can do it even shorter. We don't need the result function. We don't need the function. We don't need the std stud function for it, because we can use something that's called stud memfun, and it has a result type itself. So we don't need the functionality because it's a function itself. But please don't use it because it's deprecated since C++17. Any questions about what we saw? No. Okay, so now we can start digging into what we're going to do here today. During this talk, we will create something that will detect a container. We will start from older versions of C++, and we will gradually go on into C++20 and concepts. And bear with me, because we will start with code that is hard for people, and we will get to code that should be more readable and more human-like. So in C++11, we got a really, really nice facility in the standard that's called traits. One of the traits you already saw we had to implement it by ourselves. It's the is-same. But we have many, many more traits that are usable and very, very important. If you are using metaprogramming or generic programming, it's super important to know about this library. If you don't have access to C++20, it's even more important because it's the only thing that you have right now. Besides is-same, we have convertible, assignable, and many, many more. So just go into typetraits.h and you can see many other traits that can be used. Some traits are really simple. We already saw an implementation. That was my implementation. Inside the standard, it's implemented a little bit different. They are using inheritance from false type or true type, where false type and true type are just integral constants from type bool, and they have the value inside them, it's true or false. Some traits are more complex. For example, for floating point type, you are inheriting from an integral constant that is of type bool, and then the Boolean expression itself, you need to ask if it's the same as a float, or is it the same as double, or is it a long double. Remove CVT is another type trait that they are using, but it's a little bit more complex, not too much, still readable. Now, what can we do with those traits? We can constrain types. That's what we want to do in generic programming. We want to constrain types, and by that create correct overload resolution and select right functions for what we need to do. So here is another example before we start. Here we have a very simple function that's called print, and I really like FMT library. Anyone uses FMT library? Not too many people, but that's cool. It's a really great library that allows you to print things easily in C++. It works in compile time, some things, but it's really nice. So the print function is really simple. It's just a templated function that receives a const reference to a type, and we want to print this type. Sorry. So do you think it's a good idea to use something like that? What can go wrong, right? So there are things that can go wrong if you're using it like that. For example, here we have an integer, and we want to print the pointer to that integer. We cannot do it with FMT library. FMT library allows you to print only void pointers. I could select a different example, but this is a nice one to understand that sometimes you cannot just leave it for one function without constraining your types. So here we already have an error that maybe some of you didn't think about. How can we fix that? We can constrain the types, as I said. So there are many, many different ways to do the same thing. I have selected to do it like this, and we will use type traits. So we are creating a print helper struct. This struct receives a template parameter t, any type, and a non-template parameter boolean. So it can be true or false. Then we're specializing, print helper struct with true. So this print helper struct will be constructed only if it receives a true non-template parameter. And each one of those has its own print function, where the first one has a print function for any type that is not a pointer. But if you have received a true non-template parameter, we know that it's a pointer, and then we need to dereference it. In the end of the day, we need a function to do it, and the function itself is called print. It's just templated like the other functions that you saw, and we are using print helper struct inside it. We are providing it with a type. We are using a type thread that's called isPointer. The isPointer will get the type from inside it. We will use the value, and we will operate the function print on it. From that, the correct print helper will be instantiated, and we will print the type. And yes, I know we discarded the void pointer problem. So if void pointer will be provided in that example, we will crash. In C++ 14 and C++ 17, we got very nice aliasing for things. For example, we got an alias for the type rates with _t. _t is just an alias for the type that resides inside the type rate itself. In C++ 17, we got _v, that is just a type for the Boolean variable that resides inside the trait, so it can be true or false. Here you can see just the aliasing for @pointer_t or isPointer_v. And that's how we are using it. It's the same example, but the only difference here is that we are using the _v for isPointer, and it's less code. I don't know, I would argue it's more readable for people because it's less cluttered, but it's almost the same. There is no big difference. We can use a different approach, a little bit, again, something that is more familiar to people or easier for people to read, that is called type dispatching. So type dispatching, instead of creating structs, we can use the point that isPointer_t type itself, it's true type or false type. We already know that there are different types there. The standard already defined it for us. So we can create a function instead of a class. This function will use type dispatch, so the overload for the first function will be a false type, and then we know it's just a type that we need to print. The second function, the overload, says it's on a true type. So if a true type will be provided, then we know it's a pointer, and then we need to print this pointer. And then we still need to create the template function like we used before, that's called print, and then this function called print helper. It uses isPointer type. We need to initialize this type because we need to provide an actual object, and we are providing it with t that we want to print. I think it's more readable and easier. Yes?
So will the compiler guarantee the temporary object be removed?
The what will be removed?
Temporary object, when you create type?
The type itself?
Yes.
If it's an O3, usually yes. Usually, because it's not used, it will be dead parameter inside the compiler, and the compiler will just clean it up for you.
Okay. Is that inside standard or just a...
It's a compiler, it's not a... With C++ 17, we can do things even easier. And again, here I argue it's very readable already. You don't need to do all these tricks with dispatching and looking at types. You can just use if-const expression. If-const expression is just something that was added in C++ 17 that says, if the branch is true, I will take only the branch, and the else will be removed from the function entirely. It will not be compiled, or vice versa. If it's not true, then only the else will be left in the function, and everything else will be cleaned. So we don't have compiler errors here because we are compiling only one thing. What do you think? Is it more readable than the previous examples? Someone said no? In C++ 20, we can use our first concept that we're seeing here. This is the weakest concept of them all. It's called auto-parameter to a function. So we will go deeper into it in the end of the talk. But here I just wanted to show that we can create two functions with an overload, one for a reference, one for pointer, and we're just doing the print for ourselves. Easy, readable, understandable. But there's a problem here because we lost the constness. And just remember this example. To fix this problem with the constness, we will need to use a pointer concept. We will get to there. But for now, just think that this thing is alive and is somewhere out there in the code, and it works. By the way, I forgot to mention, all the code snippets from here are compiled. I will publish Godbolt, so you can play with the code and see all the examples. And it's not slideware, as you may call it. Okay, so now let's talk about the main event here. We want to detect a container. C++ containers, all STL containers, have a nested iterator inside it. So we can use it to our advantage. It's a very naive implementation, it's a very naive way, but each type has it. So we will need to create some kind of trait to detect it. How to do it? We need more, we need more understanding we need more tools under our tool belt to create this thing. So first thing that we need to understand is sfine, a very funny name for a very important thing that's called that substitution during a compilation for template functions. If an overload will create an error, it will just be removed quietly, and the only function that is selected is compiled, and you will select the correct function, and everything will work without a problem. The second thing that we need to know before we start implementing it is that ellipsis functions are considered to be inferior to any other function. So if we are creating a function with ellipsis, and we are creating a more defined function or more concrete function with an integer, and we are using it inside main, we will say we want to print 17, and we want to print a string of 17. So the compiler will select the more concrete function in the overload resolution. For integer, 17 is more concrete, so the second function is selected. For string, ellipsis is good enough, and we will select it because string is not an integer. Now that we know how sfine works and what is sfine and how ellipsis works, we can create our first trait for isContainer. So in this trait, we have a class that's called isContainer that is templated on a type. Then we have two functions inside it. Both of those functions are templated as well, and they're overloaded. So the first function is just an ellipsis function that returns byte. And the second function is overloaded if and only if the S templated type has an iterator type inside it, a pointer to an iterator type. Afterwards, we need to define a value. This value will be true if and only if we will call to f with a 0, because 0 can be just a null pointer. If we are calling it with a 0, and it can be an iterator, if the resolution of overload is correct and we have an iterator inside this type, then the correct function will be called, and then we know that it's an actual container or not by the return type. If the size of the return type is 8 or is 1. How can we use it? This is an idea. We already talked about it, so it's not a good idea right now. We will gradually get better, and we will get to C++ 17, and we will see how things are getting better and better with this time. But what you're going to do, what can we do right now? We can just delegate to a helper class. We can delegate to a helper method. In some cases, it's just better to just create two functions and do the overloading for you. Now, we need more things to continue and to progress and create a better isContainer trait. So enable if. Enable if is a way to force the compiler to do sfine for you. Here's an example how it's actually defined in the code, in the standard, I'm sorry. That's how it's defined in the standard. So here you can see the implementation of this thing is very similar to dispatching that we already seen. It's just specialization for something, and it's well defined if and only if the Boolean expression will return true. And that's how we can use it with enable if. So for these examples, we want to print something, or we want to print it as a container, a number or a container. So we have a print function that receives a type, and then the second parameter to this function is an enable if type that uses our isContainer trait on the type that we have received. If the trait will be fine, it will return void pointer, and it will be equal to null. The second function is an overload function that says it still receives a type, and in this case, we want it to be isContainer. In the previous type, we wanted it with a nut, if you can see that. In this type, we want it to be a container. So if we will use it with print 18 and print std array with 1 to 3, we will get this, 18 and 1 to 3 without a problem. With C++17, we already saw it. We don't have to do we don't have to use enable if. We can just use if const expression. We're using our trait. We're saying if it's not a container, just print a number. If it's a container, let's do an iteration over the container and print everything. And here as well, we have print with 2 and print with std array. And we will get number 2 and container 1, 2, 3. Variadic templates. Variadic templates were introduced in C++11, but another very important and very strong tool for variadic templates is fold expressions. In C++17, they are represented, and we can use it to our advantage. So here we will create a type trait for detecting if all types that are provided to the template parameter pack are integral. Well, we are using stud conjunction. Stud conjunction is just a type trait that helps us create a logical conjunction expression from other type traits. So we are using it here, and we are saying, let's see if all types that were provided are integral. And to work with it, we can create a function that receives a variadic pack parameter that's called check. We're moving the values inside, and we are using static assert that are using our expression that's called are all integral. And this function will work if and only if all parameters that are provided are integral. It's getting readable. Like people, I think, most people can understand what is written here. Another tool before we continue to the better isContainer is void t. Void t is an extremely simple alias template type to help us. Void t will be well formed if and only if all types that are provided into void t are well formed. Is almost the same as in enable if type, the nested type inside it, but it works for many, many types that can be provided. So it looks something like this. It's a template that receives all classes inside it, and it's using void t equals void. That's it. So simple. And luckily for us, it was introduced in C++17, and we have to thank Walter E. Brown for introducing this for us. Now, let's create our first concept. We have already seen other concepts. Naive isContainer, it's a type trait, but it's a concept. If you think about it, traits and concepts are almost the same. Are all integral are concepts as well. Auto as a function parameter is a concept. Now that we understand that, we can create a better concept for containers, for detecting containers. So there are a couple of rules that each container in C++ must obey. Each container in C++ will implement all these rules. So first rule is the container We can call stud begin on the container. We can call stud end on the container. We can compare begin and end iterator with not equal. We can use stud next on the begin iterator. Begin iterator has to be dereferenceable and not equal to void. And begin iterator and tail iterator are copy constructible and destructible. So now let's create it. And here I have to say, we're getting to dark territories, and this is going to be horrible in my opinion. Most people will just start reading these 3 lines and they say, I don't want to continue. We need to create types for our concept. So we're starting with begin. Begin is just saying, let's template it on C. Then we will use decal type on std begin of decal val from C. Decal val is something that was introduced in C++11, and it's used for creating a compile time non-complete type just to check things during compilation, to constrain the types and do something. You cannot actually use this type. Why is it good for? Anyone used decal val here? Do you like it?
What options do we have?
C++20.
I use that lot as well.
Okay, so decal val is just basically it helps us to create a type, even though it doesn't have a default constructor. So there are types T that we're not aware of. We don't know if this type has a default constructor, doesn't have a default constructor. Decal val does this job for us. Even if the class doesn't have a default constructor, it will still create something for us. It will be incomplete, but we can still check if it has a function inside it, if it has a nested type inside it. So we have to do it because std begin needs to work on an actual object. And here we are providing it with an actual object, but it's not inside an evaluated area because we are using decal type. If it was in an evaluated area, we could not use it because what decal val creates for us, it's not usable during runtime. We are doing the same thing for std end, and we are creating something that's called not equal. Not equal uses the same trick. It's using std decal val on bi, which is supposed to be a begin iterator, and we are operating not equal on std decal val, the end iterator. Then we have to create the t increasable type. So we're using std next on the decal val for the begin iterator. We need to see if the iterator is dereferenceable. So we are creating the type called dereferenceable. It's decal type for decal val for bi, and we are dereferencing it. And then we can do the first line of the actual concept that is called isContainer. It is templated on C and type name void, and it inherits from false type. Easy, right? Not this one. To create the specialization that actually checks if it's a container or not, we need to create another struct called isContainer. This struct will receive the C type, and then the second parameter will be a void T. Void T by itself receives T begin, T end, T increasable, T not equal, T dereferenceable, and that's it. That means it will be an actual void if and only if all these types are well defined. After that, we need this type to inherit from std integral concept, which is of type bool, and we are using traits from the system. We need to understand if T begin and T end are not equivalable, and the return type is Boolean. We need to understand that the dereferenceable type is not void. we need to understand that std that is destructible, tbegin is destructible, tbegin is copy constructible, tend is destructible, and tend is copy constructible. Okay, who thinks that people in his workplace, if they will see that, what will be the reaction? Yay, fun! Now let's see how we can actually use it. So we have a const expression function that's called isContainer that receive a container inside, and it will just return the type trait isContainer value. Easy. We can use it with enable if. We are saying the return type of this function is an enable if function. If it's a container, then take the C value type. That means we're returning the actual value from the container. Value type is a type that is nested inside every container in C++, and we can just return the container. If it's not a container, we can do it the same thing, is container. What am I missing? It's almost the same. So, problems, anyone? Do you see the problems here? Have anyone ever written concepts like that in C++ 11?
All the time.
Me too, but what is the problem? What was the problem back then? If you had some error inside your template, how many lines of errors would you get? You would get a scroll of errors that says nothing and it's horrible to read. I must say that the newer compilers doing a better job with it, and you're getting errors that are more defined, but still it's harder, and it's harder to find an actual error itself. Enable if and or void t by themselves are really hard for people to read. There's nothing to do about it. People are still afraid of them, and it's hard for them. And most people, when they will see this concept and they will see this code, they will come to you and say, you wrote it, go fix it. And this is how you will be after they will tell this to you, like a headache all the time. Now we're getting to the actual part, the interesting part, what we can do with C++20 to make our lives easier, and how concepts change the way that we are doing generic programming and how we are looking at generic programming. So, just like in C++11, C++20 has created the concept library for us. Inside the concept library, you have things that are similar to traits, but they are easier to use. For example, we have same as. Same as is almost the same as is same. The only difference is same as and all concepts will return Boolean expressions. So if you will use same as tu, it will return a Boolean. Integral, it's almost the same as is integral. Destructible, assignable from, convertible to. Many, many, many good concepts that you can use directly from the standard and that can help you constrain your types. Here's an example of how we're using how we can use concept in C++20. So I have already mentioned that the auto parameter to a function is the weakest concept there is. We can write a stupid function like this that's called f. It receives auto A, auto B, and it checks if A equals to B. Now, do you see any problems that might happen if you are using function like that?
Non-matching types.
That's right. So let's see an example. Now we're using foo with 1 and 1. The deduction, the type deduction will say, okay, the first one is an integer, b is an integer as well. Everything is fine and dandy, it will return true. If you will use it like this, with 1 and 1.0, 1 is an integer, 1.0 will be deduced as double. It's still fine. It will be truncated. 1.0 will be truncated to an integer, and it will actually return true. But I'm not sure that the writer of this library actually intended for it to be true.
You won't get type promotion on that in the comparison? Because it will pass them through.
It will get type promotion, yeah.
Right, so then you're comparing the 1.0 to 1.0, which may not be equal.
No, it will compare it to 1, to an integer.
Okay.
It will promote it to an integer. It will truncate it and promote it to an integer, and it will return true. If we will use it like this with 1 and a vector of ints, still the function will be called, but the problem is you cannot compare 1, an integer, to a vector, and you will get an error from the compiler. It's pretty understandable error that says, okay, integer and vector cannot be comparable. But still, the function itself will be called. How can we fix it? How can we avoid this thing? We can use those concepts from the library to constrain the auto itself. So the nice thing about concepts is they're consuming the first parameter, template parameter, into the concept from the type that is deduced from the auto. Here you can see I'm not writing any template here. I'm saying stud integral auto A, stud integral auto B. We are not providing the template parameter itself. It will be deduced and used from the parameter that is deduced for A and for B. So for me, it's already something that is more readable, that people can understand. Okay, foo2 works only on integral parameters. Only on integral parameters. Still, they can be different integral parameters. So now if we will use it with 1 and 1, A will deduce it to be an integer, B will be deduced to be an integer. Both of those things are integral, and everything is fine, and it will return true. But now if we will use it with 1 and 1.0, it will be deduced to int and to double, and now the function will not be called. Now we will get a more interesting error that template is ignored, template function is ignored, foo2 is not something that we can use. And then you actually have a nice reason why you can use it, why you cannot use it, because double does not satisfy integral. Readable error. Finally, readable error when you're dealing with generic programming. The fun thing with constraining types is you can constrain even variables and not just parameters to functions. So here is an example of how we are constraining variables, for example, inside a function. We can say that the first variable val I, it's auto, but we want it to be just integral types. So if we will use 1 UL on val I, it will be fine. The second variable, we are saying we want to constrain it to be only float types. It can be any type of float, but it needs to be a float. So if we will use val f equals 1f, everything is fine. But if a line after that, or somewhere inside the code, we will use another variable that we are saying we want it to be only float type. It's an auto, but we want it to be constrained to float types only. And we call it val f2, and we want to assign val I to it. It will not work. This will not compile, and this will not compile because unsigned long does not satisfy floating point. So this will make C++ safer. Instead of fearing all the implicit conversions that usually happen in C++, you don't have it here anymore. Everything is constrained. We just need to start using those things more. Okay, so until now I showed how to use the constraint from the standard library itself. But it is really easy to create your own constraint, your own concept. The first thing we will see, it's a basic definition of something that's called name concept that uses a constraint expression. And the definition of the concept is really simple. We are starting with a template, then we are saying concept, we are giving this concept a name. In this case, it's convertible to int. And inside the constraint expression, we are saying this concept will be satisfied if and only if the type that we are provided will be convertible to an integer. There are more things that we can do inside the constraint expression. We can do conjunctions of many constraints. So here we have another concept that we're calling it convertible to int or not double. So we're using the convertible to int that we are defined before. It's a name constraint. And then we're saying, and it's not same as double. So we can receive anything that is convertible to int, but if it's a double, we will not be satisfied. Same thing can be done for disjunction. Just instead of a and, we can use it with an or. So we are saying we want a type that is an integer or larger. So same as int, or size of the type that we received is larger than the size of an int. Another way to use constraints is constraint expression is with something that's called atomic constraint. Atomic constraint is something that is created when concepts get normalized. Normalization of concepts is saying, okay, let's take all the named concepts, let's take all the required expressions, we will get there, and let's convert them to something that is atomic expression. Atomic expression, it means that you have an expression with a template, and when we are putting the template parameter inside it, it should be deduced to a Boolean expression. It cannot be convertible to anything else. It has to be a Boolean. So if it will return an int, it will not be satisfied. All the expressions in the end are, after the normalization process, will be atomic. But we can create our own atomic expression as well. So for example, here we have a class called SC that has just an operator, parenthesis operator, one that returns true, the other that says that if it's a bool, it returns false. And then we can create a concept called AC, that is SC with a T that we received. We are creating the type, and we have to use the parentheses. We have to use the parentheses because atomic constraints must return a Boolean type. If we would just use SC and create a type itself, it will not work. That was the basic constraint list. We can constrain types even without creating a named concept. So what we're seeing here is basically we're saying we want to create a struct that will be created if and only if the template type that the struct is templated on will be larger than an int. To use that, it's something that's called require clause, and to use that, you can use the require keyword, and here we have to use parentheses. Inside require clause, we need to use parentheses because require clause must be used as primary expressions. Primary expressions, do you guys know what primary expressions are? Okay, primary expressions are literals, things that are global. Boolean, for example, true or false is a primary expression. Parenthesis operation is a primary expression. Fold expression is a primary expression. Lambda function is a primary expression since C++17. And require expression is a primary expression since C++20. We will get to that in a moment. But here is an example. So as you can see, we have a function here that returns a bool. Everything is fine. It's a const expression function. It always returns true. But if we want to create a require clause with this function, we're saying here almost the same thing. It's larger than int. So we want it to be larger than int, and also return true should be true. Basically, it looks fine, right? But return true with this call is not a primary expression. It's a function type. To fix that, we just need to put parentheses around it. So parentheses expressions are primary expressions. It will get here, it will deduce if it's true or false, and then it's just gonna be an atomic expression, primary atomic constraint, and it will get us a true or a false. Okay, Now we're getting to require expressions. So we had constraint lists, we had require clauses, and now we have require expression. In my opinion, require expression is the strongest tool of them all, because you can see here, it does a lot of work that we have to do in C++ 11 to 17. It does the work for us. So from what you can see here, to create a require expression, you need to create a concept. Here we are creating not equal on concept on begin iterator and end iterator, just because we're looking at concepts to detect containers. And here you can see how the require expression needs to be defined. So you're writing requires again. Requires has many meanings in concepts, but here you're starting something that looks like a regular function. You're providing it with parameters of type bi and type ei, and basically what the compiler does for you is creates the decal values here, and you can use them without all those jumping through hoops, and just use those types. This type of expression is called compound expression. So what we are trying to say here is, can we use bi not equal to ai? And will the return type from this expression be convertible to bool? What do you think? Is it readable? Is it understandable what you are trying to say here? Okay. Now, let's look at this example. So I want to create a very, very, very simple concept with a require expression that's called my same is. It's very stupid, it's very simple, toyish. It uses a require expression, and then we are saying that std same as t in u must be valid. And then we're using it inside the function. We're saying, okay, auto x can be anything. And then only if y and x are the same, the function should work. Inside the function itself, we have static assert for same as decal type x, same as decal type y, and then we are executing the function with 1 and 1 UL. What do you think will happen here?
Static assert will fail.
Correct. Static assert will fail because, why?
Because you're checking the validity of the expression same as rather than actually checking if it's true.
That's correct. So basically, what's your name?
Patrick.
What Patrick said is absolutely right. When you are writing a requires expression, if you're writing something inside require expression, it just said, will this be valid? It's not evaluating it at all. But if we actually want to fix it, we have a way to do that. We can put, surprise, another require. Like everything in C++, the same word has many, many meanings. So it's just hinting to the compiler and says, okay, I don't want you to just say, can I do this on those types? I want you to actually evaluate it and to say, is it true or is it false? And now when we will use the same function with the same parameters, we will get what we want. It will fail because we cannot call this function at all. Another thing that we can do with a require expression is to check if type is well defined. So here is a concept that's called type check. It has a require expression. Note that we can just create a require expression without the parentheses. We don't have to create parentheses if we're not actually using the types inside it. I mean the decal val objects inside it. So we can check if the type t that we have received has a nested type called type inside it, and if sc, if you remember, we have created a type that's called sc, with t is a valid type. So it will check for us if both those types are actually something that we can use. And only then this will be satisfied. Again, there's another meaning for requires. And if we want to do something like require clause that is ad hoc, we can use the same thing for require expression to make something that's ad hoc. But surprise, here you need to write requires twice. So if we are putting it inside the template, and then we are saying, okay, this type has to operate with a not operator on it, we are putting requires, then we have the parentheses, not t, and this struct will be constructed if and only if the type that is provided to it can be operated with not. And like everything in C++, there's wonderful things that you can do. So we can replace all the required clauses and all the required expressions all the required clauses and all the constraints list with ad hoc requires. So here we can see all these wonderful things. We just replaced everything with requires. It's an ad hoc require. Then we are saying, okay, I want to evaluate is pointer v inside here. And then we are opening another require ad hoc. And then we are saying, okay, I want it to be convertible. And then I want another require clause. And then we have all the smileys inside it. And like David Stone said last year in his lightning talk, it will make your coworkers smile. I hope it makes you smile as well. A question, Luke?
Can you put the template keyword inside the nested requires to introduce additional types?
No. It has to work already on something that is trailing. So you cannot start a new template inside the require expression. But it made you smile? Yeah. That's the most important thing. Okay. So now we talked about how we define concepts and what we can do with concepts. Now we need to understand how to use concepts. And again, like everything in C++, you can express the same thing with many, many different ways. So a reminder, we had this not equal on concept that does the not equal on bi and ei, and if the result is convertible to Boolean. How I can use it? We can use it inside the template parameters themselves. So here we're saying we have a function that's called fun that returns true, and this function will be called if and only if, type name ei, and not equable on ei bi. It's just we're expressing that we want bi to be a constraint type on end iterator. So only if not equable will be satisfied, this function can be called. Another way to express the same thing, by the way, I wanted to say one more word about it. I have switched ei and bi because as I mentioned, not equal on will consume the deduction type as the first parameter to the concept itself. So I want it to be the same. I want the first parameter to be the begin iterator and the second parameter to be end iterator, as specified here. But the function itself is called with bi and ei as you would expect it to be. Another way to express the same thing is to call it with require clause after the template itself. So we have bi and we have ei, and you have requires not equal on bi and ei. It will be satisfied only if bi and ei are not equable. And here we don't have to do the inversion of things because we are providing both of the types. Another way to express the same thing, another way to express the same thing is to put a trailing require after function definition. So we're almost saying the same thing, but this is after the function definition. We're saying require clause that it's neck on bi and ei. You can use it in a different way, in a different situation, but you can do that. It's the same. It's the same as putting it here in this function. But as you can see, you can do it in many different ways. So, in my opinion, in this case, this one this one is the best way to go in this case, because you're saying it's a template type. You don't need to provide anything here more than is specified. and it's more understandable. You're saying, okay, it's templated on EI, and it's not equable type. It's already a type. But there are cases that you actually need to use the required clauses after the template definition, or after the template definition, or after the function definition.
So this one allows you to use the variable names, I guess.
Yes.
That's the case.
And this one as well.
You shouldn't need in principle.
Yeah. And another way to do it is already something that we saw. We can actually constrain the type for the auto. So here in this function, it's auto BI, and then we are saying EI should be constrained on not equal decal type of BI. It's something you can do. In this case, I wouldn't do it. Here's an example of the usage for this thing. So we are calling to fun with 1 and 1 UL, and this will not work because, sorry, what happened here? Something happened here, so I'm sorry. Now we will call the function with 1 and std vector of 1s, and we will see that we will get a problem here because the types that we are using, EI and BI, cannot be used. We cannot see if it's not equable. A vector cannot be not equal to 1. We cannot use not equal operator on those types. Okay, let's return to something that we've done before. We have this C++17 style concept that is using std conjunction, and it is used inside the function. We just talked about it. Let's create a C++ style concept for the same thing. So as you can see, it's already shorter and better, I think. But what do you think? Is it a good way to use concepts? The answer is not so much. It will do the correct thing. It will fail when it needs to fail, but you have a problem here. The error message just tells you, listen, conjunction V return false. You don't get anything here, but you can get more. And why you can get more? Because there is something that's called partial ordering of constraints. Because, as we said, concepts get normalized, and all concepts are normalized into atomic types. It means that if we will get more concepts that the operation can see, it can tell us more about the types that have failed, and we can explain, we can get better error messages and more information. So to fix it, it's really simple. Instead of using the conjunction from C++17, we are just using a fold expression. We are saying, okay, if all types are integral and ellipsis, we're expanding all the types here. All these types are basically just named concepts, and those named concepts will be stripped down to atomic expressions. And now, if we will use the same function as we used before, we will get a better error message. We will get, okay, you call the function with int, and double, and it failed because double does not satisfy integral. So you have more information, and this is the better way to use it. But you can do more with partial ordering of constraints. It actually helps us to select the correct overload during overload resolution. So here I have a short example of a class that uses a non-template type K that's called doStuff, and it has an explicit operator string view that returns the string. Then it has private functions, that the private function is called getStr, and then we're using a require clause that says, okay, it requires for the K to be integral. That's it. Then we have some require clause that subsumes the previous clause. So this clause will be more defined, more concrete, and inside the overload resolution, the more concrete function will be used. So what we are asking for it? We are saying, okay, this one must be integral as well. but k itself should be larger than the maximum number that can fit inside short. This is a more concrete function. And then we have another function that says, okay, if it's not an integral, that if it's convertible to string view, just use the string view itself. Then the usage, we're using std string, we're calling the function, and the compiler will do the work for us. So to use it, we're doing stuff with std string view on do stuff with 10, and this one will print 10. That's it. But if we will provide something with limits of the short and the maximum number that can fit the short type, it will print the second function. So it will print, okay, the main value is 39, the multiplier is 1024, and we will get the values. So again, it's very, very important to use partial ordering on constraints because it helps us. It really helps us, not just to get better errors, but to get better resolution for our overloaded functions. A reminder, do you remember in the start, I started with a problem that we cannot use something like this. We cannot say autoconst reference to a value and then just create another function with autoconst value with a pointer because it will not work. So why won't it work? Let's look at it. The compiler will start initializing those functions. So it will say, okay, I have a print with int pointer, and int pointer const reference val is a valid overload. I can use that. Then it will create another function with int pointer, and it will say, okay, is it an int pointer const pointer value? This is a valid overload as well, but the type that we are providing is not. It's not a pointer to a const area of a pointer. It's just a pointer, and it can actually fit only to this function with a reference. So we are failing there. And we will try to print just a type, even though it's a pointer. So how can we fix this thing? We can say, okay, we can help the compiler and tell him, this is an integer. So it will instantiate those functions with an integer, and then there is only one overload that is fine for it, and it is int const pointer. And then we will get the correct type. But think about it. Is it something that we want to use? Think if we have more than one type, we have 5 types, or we have a variadic pack of types, we cannot use this anymore. A second way to go is to tell the compiler, okay, I have a type of an integer type, but I want it to be a pointer to a const int, j. And then we will call the function with the j instead of a reference to an I. The compiler will instantiate this one. Everything will be fine and dandy. But again, we have the same problem. We're helping the compiler too much. We don't want to do this. We want it to deduce the types correctly for us. So here we go. This is what we actually need to do. Here I wanted to show you how to do that we can do a constraint list with a named constraint, and we can use a require expression as well. So here we're saying, okay, a pointer is something that is the same as void pointer, or it's something that is dereferenceable. And now, if we will use it like this, everything will be fine. Okay, let's return to the concept that we all gathered here for. Let's create the container concept. We need to create the concept for the things that we need for the things that the container needs to provide. So we're saying not equal begin and end. We have a require expression that receives a container. We're saying with a compound expression, if begin not equal to end, and the return type is same as bool, only then this will be satisfied. Then we have to create another concept that's called has begin and end that receives a container, and it will be satisfied only if this type C, if std begin and stud end can be called on type C. Another thing that we need to create is to see if it's incrementable, if the begin iterator is incrementable. So we are getting the C container type into the required expression. We are saying, okay, please see if C can be used inside the begin, and then we will use ++ on it, and it will be satisfied if and only if it's something that can be done. Now we need to see if it's dereferenceable begin and not void. So again, it's a required expression. We are saying, okay, we are receiving a C that should be a container, and now we want it to actually to be evaluated inside the required expression. So we are saying it requires for it to be not same as decal type of the reference for begin of C and void. The final thing that we need to do is create a concept for begin and add copy constructible and destructible. We're receiving the same C container. We are evaluating if copy constructible, copy destructible, copy constructible and destructible for begin and for end for C, they are valid and working. And now we can create the actual concept. So we're saying template type C, concept container, has begin and end, incrementable begin, yes, dereferenceable begin, not void, and begin and end copy constructible and destructible. In my opinion, this is something that is shorter, this is more defined, this is something that more people can read. It's more self-explanatory because you're giving it names, you're giving it almost function-like feel, and people should be more familiar with those things, and thus I think they should be less afraid of them. So how can we use it? For example, here I'm creating a function that's called isFirstElement, the same, and we are providing container out of C, container out of C2. This function will be available only if those two things are containers, and then we can call equal operator on the dereference of begin and the reference of begin of C2. Why is it okay? Because we already know that those are containers and they have those things. So if we will call it with vector and array, isFirstElement VA, and we will return 1 or 0 according to the Boolean that will be returned, here we will get true. But if we will try to do the same thing with vector and a tuple of the same numbers, and we will call the same function, we will get an error because this function is not valid. Why is it not valid? We're actually getting a normal error message that says, hey, you cannot use has begin and end on a tuple because it doesn't have a begin and end. And then you can go and actually understand why. And it's actually providing it for you. It says std begin cannot be used there. Okay. So for conclusion, concepts making our life for generic programming easier. It's easier to read. It's easier to write. It's easier to understand. Lately, I start hearing people saying that concepts are complicated. And it's really hard for me to understand why, because if you know the history and you saw what we saw here today, how hard it once it was to create almost the same thing, and how easy it is to create the same concepts now and to use it correctly and to get the results faster, more readable, I really don't understand why. I will finish with showing you the difference between the first one and the second one. Just from here, you can see that it's something that is bloated up and it's horrible, and maybe it's going to be really hard to debug because you have void t here. It's unreadable for most people. The std integral constant itself, it's something that is harder, and it's harder for people to understand. And here you see something that is very small, that is self-explanatory. It says exactly what it's going to do. It's going to check for us if it has a begin and end. It's going to be incrementable begin. It's going to be dereferenceable and not void. It's going to be begin and end copy constructible and destructible. Everything is understood here. And as the robot says here, yes, it's 83.6% readable. Maybe we can get better than this. I think we can get better than this. But it is much better than it was before. It is much better than what we had to do, all the tricks that we had to do in C++ 11 to 17. So in the end of the day, use concepts. Use them in your code base. If you can, if you have C++ 20, move to those things. If not, as I mentioned, compilers, newer compilers have better error messages, but still, it's going to be harder for people to read those things. And that's it. Any questions? Yes.
Yeah.
Yes, Luke.
Are there any resources to get the legacy concepts defined using C++ 20 concepts?
What do you mean?
Like the before C++ 20 has actual concepts that you could write. The standard has the concepts of a forward iterator.
Traits, right?
No, like the concepts.
Like you can turn any context into a concept with a one-liner, right?
Yeah.
Right.
Okay.
So you can use, like I showed a couple of things that how we use them in C++ 17 and how we're translating it to C++ 20. Almost everything that can be done there can be done easily with C++ 20. The only thing you need to keep in mind is the partial ordering and the atomic expression and those things, because they will help you with the concepts. They will help you with the error messaging, and they will help you with the overload resolution. Yes?
I think the killer feature of concepts is the subsumption, not so much the syntax, but personal opinion. Do you know a way of simulating subsumption without C++ 20 or add concepts using all techniques without you doing this and this, but not that and that and that?
As I showed before, you can create the traits. You can create traits that do similar things, but you need to do some jumping over hoops to do that with tag dispatching, enable ifs, void t, those things. You cannot do the subsumption without concepts because it wasn't in the language. So you had to do those tricks before then. Yes?
So I agree with you on almost everything.
Almost.
Apart from the partial ordering, because I think it's quite easy to screw it up. Because the rules for the partial ordering of the concepts are very precise, and the moment you pack something in, because you think, oh, it's more concise to write it like this way, and because it won't look inside. The moment you pack something into a concept, it won't be packed out again.
That's right.
Analyze. So you have to be very explicit to write the correct partial ordering.
Hey, but we are using C++. What's simple in C++, man?
Yeah.
You have to understand those things. Yes, and if you will read the standard for partial ordering, it's horrible. I can say directly, it's horrible. You can almost not understand what they want from you. But those simple things, those things that you need to do, you can understand that you need to expand those things. You need to use those things a little bit better, and you will get more information from it. So if you can, do it. If you can't, that's okay. You will still get the error. You will still get the constraint. It will be less nice. It will be not as nice, but you will get what you want. Yes.
No, I mean, following up there, I think that now it's too easy to try to implement the right concept and write it well, both things. I mean, I know that this container is an example here, but probably it's not the concept you wanted in the first place. You wanted its range or something like that. So, you know what I mean? It's like, I know it's a good example anyway, but you know what I mean? It's like, it's too easy to go overboard, and that's much more than you need all the time, and implement it in the wrong way because you ask for more than you need.
But I think that it's harder to implement it the wrong way now.
Yeah.
So if you would implement it, again, in C++ 11 to 17, you would get more problems. You will get worse error messaging. You will spend time and time on debugging your template code, where now it's more explainable. It's more, you can understand it better. So it's easier to create harder things, like you're saying, something that is going overboard, but it's harder to do something that is not correct. If you understand the rules, and as I walked over this PowerPoint, this presentation, there are a lot of rules. You have to understand what required means in which way you are using it, because it means many different ways. But still, it made our lives easier. For me, again, I'm using metaprogramming all day, every time, and I'm developing libraries, and almost our libraries at work, they're using 70 or 80% compile time expressions. So for me, moving to C++20 was a must. It's hard to maintain a large code base that is templated, and then you're getting errors that you don't understand. Well, most people. And personally, I'm a group manager for 30 people, and I don't want each one of them to come to me and say, hey, Alex, what does that mean? They need to understand it by themselves. So that helped. I have to say, moving to C++20 changed our work day. So people understanding the errors now, and they can create better things. Yes?
Just one remark, though. My mental model about concept is before it, template metaprogramming was simply untyped. And now with concept, we have typed template metaprogramming.
Well,
In a sense.
don't call it metaprogramming.
Yeah, compile time.
No, don't call it compile time programming. Note that I didn't use metaprogramming, almost never used metaprogramming during this talk. I said generic programming, because all we did here is generic. It just to constrain a type, to use something with a type. Metaprogramming is actually creating something during compile time, calculating something, using algorithms. This is not metaprogramming. I almost said nothing about metaprogramming here. It's generic programming. And generic programming became simpler due to concepts. Yes?
Is there a compile time difference between metaprogramming, traditional sense, and concepts?
Well, in the beginning, in the older compilers that concepts were used there, they used to compile a little bit slower, but now you don't see this, almost don't see this problem. And the code is not larger, it's the same because the compiler cleans everything for you. So in the end of the day, use concepts. Yes?
Is it possible to check if two concepts are actually the same concept?
If two concepts are the same, that's a good question. I have to check that. Never try to do that. Yes?
Is the standard library converting some concepts in later versions of the standard?
Well, I just entered the committee like 3 months ago, so I'm not familiar with everything yet. But we have people here from the committee. Chris, do you know something about it?
I'm not in the library.
Oh, so anyone here from the committee and knows? I guess not. So sorry, I'm not sure. Anyone else? Yes.
Talking about implementing it wrong, can you put because the original motivation was to make the range for loop work. Can you put the for loop range loop inside the requires clause, or is something that?
Oh, no. Require clause has to be something that is const expr. You cannot use something that is not const expr there. So you could create a function that uses that and then call this function, but this function has to be a const expr, and then you have to provide a parameter that is const expr. It is harder, but it is doable.
But the syntax has to be valid. It doesn't matter whether it runs or not.
That's true, but the syntax has. You're talking about require clause or expression? If it's an expression, it just has to be a valid syntax, something that can be done. It's not a syntax, it's just something that can be done. So can I create a type that's name is Chukumuk and with this T? So yes, because it's not evaluated, then you can do everything that you want with it. If it's not evaluated, it's fine.
It's got to be an expression, though.
Yes.
For loops, because it's a statement.
Right.
What if you put it inside lambda?
A lambda is an expression, is a primary expression.
I'm not exactly sure this lambda body would be evaluated by that. I cannot answer on top of my head.
Again, I think if you want to use something like that, you need, as I mentioned, you need primary expressions. You always need to think about primary expressions. So lambda is a primary expression since C++17. So, but it's better to use maybe a function or something, and inside the function body, you will use what you want, and it will be fine. Anyone else? Yes?
Related to primary expressions, val for an unused function parameter. Is there an alternative
For decalval,
for decal val for a function parameter that's unused?
if it's just a function parameter that you need to use, like call the function with it, but we will not use it because you cannot use it. It's not something that you can use. No, concepts are not helping you with that. Concepts helping you with, if you want to check something about the type, you can use require expression. It will do the job for you. It will just provide the incomplete types in, and then you can use them. Anyone else? Yes.
Another thing that makes subsumption kind of hard to rely on, or the partial ordering, is current compiler implementations don't support subsumption over fold expressions of logical operators. So I've come across that issue one time, and it was really frustrating.
Yeah, that's a primary expression. Or primary concept then, the fold expression. It won't look inside yet.
Right. But in the specification, it's supposed to, isn't it?
I just show you a fold expression that it looks inside it.
Yeah, but you can't do the partial ordering on the fold expression.
You can,
If you have an overload set, then it's ambiguous.
right, that's true. That's true. And then it's ambiguous if you have, if it's almost the same concept, it can be ambiguous to the compiler. I didn't want to go in it because the conversation here, the talk here is too long as it is, so. But there are more rules, guys. C++ has many rules.
Doubling every 3 years.
Yeah. It makes things easier, but then harder.
Job security.
Yeah. The smile part. That's how I write. Only smiles. Everyone smile.
Can you do, those aren't smiles, those are winks.
It's even better, right?
They're a little mischievous. That's not a normal.
But it works, it works. People like it. Anyone else? Yes?
Are the smiles still there after you run the plain format?
Yes.
It depends on the format, of course. But they will always be there, you know, but in a different order. But the order is important for you to smile more. Okay, thank you, everyone.